Okay, any questions about this picture? Okay. Actually, I want to add even more about this picture, to this picture. So what is, again, we have this operation, if f then minus. What does that do? Well, it's a negation in the direction x star, and it's like a nothing in all the other dimensions. So it's a reflection through, it says right here, it's the reflection through the plane perpendicular to x star. So the x star is like somewhere here in this two-dimensional plane. There's like a d minus one dimensional perpendicular plane to it. And that d minus one dimensional plane cuts this mystery two-dimensional plane like this. Cuts it like kind of exactly in half. That's a right angle. So how do I know that like the plane perpendicular to ket x star, when intersected with this board, splits this exactly in half? Yeah?
In some sense, it goes from like plus one of that to minus one of that, and then the plane is at like 0 of that.
There's a lot of that in that sentence.
The uniform one is like in the x star dimension is like 1 has 1 at all. Well, the 1 over root d, and then f has minus 1 over root d, and the plane is 0.
Yeah, I think I see what you're saying. Yeah.
Maybe what I had in mind is that how do we get, unif is like some vector, true. But how do we get ket f? We got it by applying if f then minus to uniform. So we did this operation, reflection through the plane perpendicular to x star, to unif, and we got the ket f. So like we did this reflection through whatever this dashed green line is. If you reflect uniform through it, you get to ket f. So that means it goes right between them. Does that make sense? Okay. So now let's come back to here. Like, now what? So ideally, we would like to get our state vector. Like, an ultimate dream would be if our state vector became ket x star. That would be amazing, because then we would just do extract all, and with probability 100%, we'd see x star, and we'd be like, solve it. So what do? We kind of prepared, by line 2, we kind of got our state vector to uniform, which is actually super far from x star. And then we did if f then minus, which reflected us here. It kind of looks like we got even further from x star. What can we do? We could do if f then minus again, but that would be pointless, because that would just take us back to unif. So what else could we do? Well, maybe this is the one. Yeah, what else can we do? We're trying to get f closer to x star. This is maybe the one part where you need an idea, but it's a minor idea. This is kind of Grover's idea. Reflect across the uniform vector. Reflect across the uniform vector. Now, you may, of course, be asking, okay, algorithmically, we have to do this. How can we do this? But that was the point of the first, 25 minutes of the lecture. Remember, in the first 25 minutes of the lecture, we talked about this operation of reflecting across a vector. And we said that, hey, as long as you have, code that can make this vector, then you can, write, convert it to code that does this operation, reflect across this vector. And this is easy to make. In fact, this demonstrates it. We literally just made it back up here. Okay, so this is easy to create from all zeros. You just do Hadamard all. And therefore, by the early part of this lecture, we saw can, easily code this. In other words, like this is literally order and quantum instructions. You do Hadamard all, and then you do if the OR of all the bits, then minus, and then you do Hadamard all. That's because Hadamard is its own undo. Okay, so we put that in our pocket just so I could say, like, now we want to do this instruction. And why? Oh, man, I drew such a terrible circle. It's terrible. The reason is, like, okay, after line 3, we got to state ket f, but now we're going to reflect across the uniform, and we're going to be, like, become at angle sort of positive theta. Like, this is, state after line 4. And you can see we kind of got closer to x star. Pretty good. Now, let's look at these two let's look at these two lines of code together, line 3 plus line 4. I'm going to put line 3 plus line 4 in a box, and I'm going to call this box R. Okay, so I'm just calling these two, this giant composite instruction, 3 and 4, I'm going to call it R. And R is a combo of two reflections. At least within this two-dimensional plane. Actually, remember, it's reflections of a different type. The first one is reflection through the d minus one-dimensional plane, which intersects the board on this green dashed line. And the second one is actually reflection through a vector, which is like, this horizontal vector. But within this two-dimensional space, it's a combination of two reflections. And it's a combo of two reflections at with axes at angle theta over 2, actually. Because like it's this between the green and the red is theta over 2. So I doubt if you remember this all the way back to lecture 10, but in lecture 10, we thought a little bit about two-dimensional geometry, and we noted that the combination of two reflections is a rotation. It's a simple fact. Two reflections equals a rotation. And how much of a rotation is it? It's twice the angle between the reflection axes. So we'll see it in the picture in a second. If you forget this, it's okay. But like we saw in lecture 10, this means it's equal to a rotation by 2 times theta over 2, which is theta. And we can see this from the picture, actually, right? So like after line 2, we got to this red uniform. And then we effectively did R, and it went like whoop, whoop, but it overall got rotated by theta. But now there's a natural thing to try to do. Somebody want to suggest it? Yes?
Do R.
Yeah, just do R again. So say we did r again. So we made like lines 5 and 6, like do r again. Okay, every time we do r, it's like order n operations. Well, I'm telling you, it'll rotate by another theta. So this is after line 6. Or after 2 r's, if you will. And just to see it like broken down, like this is not going to work well on my diagram, but like how does r really work? First it does if f then minus, which reflects through this green dashed line. So the state vector actually goes way down here. And then it does reflect across uniform. So then it goes like directly vertically up. And that's how it gets there. But now this is really good because it's rotating towards x star. And it's rotating by like theta every time. So starting from uniform state, ket unif, and applying repeatedly doing r, we rotate, theta, and then 2 theta, and then 3 theta, and then 4 theta towards x star. Now remember, okay, this diagram is not great. It looks like we're almost there. But remember, like really theta is like microscopically small. So we're actually making really tiny progress. We're not there in 3 steps. So actually, if our true goal is to get to ket x star, what is the exact angle we want to totally rotate by? Starting from uniform. Yep.
Right, exactly. So
this green dashed line is exactly orthogonal to x star. So this is a perfect right angle. But you see, the uniform is like a little bit close to it by theta over 2. Okay. Now, so the total desired angle of travel, if you will, from like uniform to ket star is 90 degrees minus theta over 2. Now, on the other hand, like 90 degrees is 90 degrees. It's 1/4 of the way around the circle. So if you're into tau, it's this. Or if you're into normal radians, it's like pi over 2 minus theta over 2. But this is like a regular number, like 1.7 or something, 1.5. This is like literally like 2 to the minus 1,000. Okay, so this is unbelievably close to just 90 degrees. So it's ridiculously close to pi over 2. And so, therefore, the number of times we should repeat r is basically pi over 2 over theta. Now, theta is still up there on the board. Theta is extremely close to 2 over root d. Now, if you're actually worried about this, you can actually literally exactly calculate theta. Like you knew this vector has length 2 over root d, so this arc length is like a tiny bit longer. If you want, you can exactly calculate that as the algorithmic designer, but you don't have to because it's extremely close to this. All of which to say is like you know exactly the number of rotations you want to do. You can even save this if you want. There's only like one minor catch, which is that this might not be an integer. And like, you can't do it like a non-integer number of times. You have to do it an integer number of times. But like, if you're climbing up to like pi over 2 by increments of theta, yeah, it might not exactly hit pi over 2, or it might not exactly hit this, but it'll be off by like plus or minus theta over 2. So like, eventually you'll get to like either, here or here. and the difference is like theta over 2. So it's basically negligible. So that's it. And what is this? This is, pi over, okay, this is basically pi over, where's theta? Here. It's like pi over 4 times square root d. Okay, I don't know what pi over 4 is, but it's less than 1. And this is, d is 2 to the n. Oh, I erased it. Okay, and that finally is where the square root 2 to the n comes in. So the actual time complexity, I'll write down the whole algorithm, but the actual time complexity is basically, you have to do r, which is order n instructions. Oh, it's not, okay, it's order n plus m. I'll come back to this in a second. But it's, it's like not very many instructions. This is the main bottleneck. You've got to repeat r square root of 2 to the n time. Okay, so I'll just, for clarity, write the whole algorithm. Oh, and then finally, when you're done, of course, you measure. And since you pretty much basically get 100% of your amplitude on x star up to some theta, which is exponentially small, you have basically a 100% chance of reading out x star, the unique satisfying string. Okay, so finally, here's Grover's algorithm, just in a box. Let's even kind of copy it here. But anyway, new qubit, B1 through Bn, Hadamard et al. That makes unif. And then, I don't know, for t equals 1 up to, technically, floor pi over 4 times square root 2 to the n. Do this r. Okay, where this is r. And then extract all. And, this prints x star, except with probability. I won't do the little calculation. We'll maybe look at it next time, but with probability less than 1 over 2 to the n. I think that's the failure probability. And just to count the number of operations, okay, this is like order n. Well, I can write it here. This is order n. This is order n. I mean, it's n, actually. This is actually n. This is n. This is where the main factor is, square root 2 to the n. And how much is this? In order to do this, you have to run the code C inside. Actually, you have to run the code C twice. So this is like 2 times m, where m is the number of lines in C. And then this also requires like n more lines. So technically, this is order m plus n, but we're not going to really worry about this too much. It's kind of swamped by this. That's order n. So yeah, the final running time, if you want to be really precise, is order m plus n, which don't worry about it, because you got root 2 at the end here. Okay, that's it. That's Grover's algorithm. You saw it. And we're going to have a whole lecture reflecting on it on Thursday. So see you then.